will learn how to use this formula. And then, of course, I'll have it on the quiz just to check to make sure you know how to use the formula. But short of those two things, you will not use this formula again for a while. And other than this formula, what is going on with this crazy thing?
This wall, I found my favorite pin yesterday.
I'm glad you did. That's
I
fine.
don't think so. I thought I lost it.
I bet that saves you a lot of time too,
What?
being disorganized.
It does. At least when the technology works.
Yeah. Oh.
When it works.
You were saying?
It's working now. I'll put my blessing on it. Oh, that worked. Yeah, it did.
Okay, that's still not what I want. Let's try that again.
Oh, that's not what you want.
All right, this one. I clicked the wrong one.
No,
We will use the chart, just not yet. All right, give me the little warning. I need to click OK on.
I'll see the best year in high school.
What is?
2015.
Really?
Oh, freshman year?
No,
Oh.
this senior year.
Dang, my fault, man. God dang.
It was y'all's 8th grade year.
Oh, was we in the 8th grade that year?
Yeah.
You
I don't go by years, I just go by grades.
say.
Wait, no, 2015 to 16 was freshman year. Not a good
For
year.
real?
Yeah, 16, 17 sophomore year, 17 to 18 junior.
Yeah, that year
18 and
was
19.
All right, what's that white block
cool.
that's there?
World history, like.
There we go.
that year.
All right,
Oh, yeah,
so-
I remember.
What was yesterday? Wednesday? Tuesday. On Tuesday, when we were talking about this relationship between frequency and wavelength, we talked about an equation. All right, somebody tell me what the equation said. Yep, exactly. All right, so we wrote down an equation that said C equals lambda nu. All right, so when we did this, we said C was equal to what?
The speed of light.
The speed of light. We gave it a name and we gave it a number. And I told you on Tuesday that you had to memorize this number. This number is a constant. It never changes. So you're always going to have that number when you plug into the formula. Now, the thing about this number is this number is given to you in units of meters per second. The problem you're going to have is wavelength, which is here, is wavelength is usually going to be given to you in a different unit. Wavelength is usually going to be given to you, and let's just use an example of 400 nm. Nm stands for nanometers. Some of you might be familiar with nanometers or nanoscience. Nanoscience is the study of things that is very small. Okay? We're not going to spend any time talking about that today, but we've got to be able to change nanometers into meters to be able to solve the equation. Okay? Now, nanometers is not part of our King Henry died by drinking chocolate milk because nano is so far out of that range. So you have to learn how to change nanometers into meters. So 1 meter is equal to 1 times 10 to the 9th nanometers. Okay?
Will we get smaller than that?
Yes, you can go to pico or picometers, which is to the 12th.
The what?
Picometers,
Picometers.
which is to the 12th.
That's gross.
Okay?
Pico de gallo.
Pikachu.
P-I-C-O. Micro.
Pico de
All right, pico. Yes, you're supposed to write all this. Come on, I don't want to have to wait all day. Now, so if we have 400 nanometers, how are we going to make that conversion? You guys have been doing conversions now for quite some time, so this should not be a hardship for us. So if we have 400 nanometers, what do we do with it?
Times it by
Put it in a what first? You might be able to do it in your head.
Chart.
All right, lots of you can do it in your head at this point, but not everybody. So put it in a chart. All right, what goes on top? Remember, we got to get to what? We've got to get it to meters. All right, so who's bigger?
Meter.
And if you don't know, just look up here at the relationship I gave you. What's beside meters?
1.
1. What's beside nanometers?
1
1
times
times
10.
10 to the 9.
1 times 10 to the 9th. So in order to do this formula, there's 2 relationships you have to learn in order to do this. So when you divide, I'm doing the math right in my head, it's 4 times 10 to the negative 7 meters.
Yeah.
Okay. Now, our units match, and we'll be able to plug in to the formula. Okay? But in order to use the formula, we have to change the nanometers into meters. Everybody with me on that?
Yeah.
So, in order to do this, we're going to have to memorize meters to nanometers and the speed of light. Those 2 numbers that I boxed in that orange color, neither of those are on the reference table, and they're both numbers that we're going to have to learn in order to use this formula.
Like by tomorrow?
Yes,
Oh, yeah.
I could lie, but yes,
Okay.
Thank you.
you're welcome. Yes. Now, the second thing we're going to be able to need to do is find the color of that light. Okay? It's not that exciting. Now, if you look at your reference table that you have in front of you, okay, your electromagnetic spectrum on the back page, the colors are displayed in the visible spectrum.
Oh, okay.
As long as it's visible light, it will have a color. Now, if it's not visible light, can you tell anyone the color?
No.
No, because you can't see anything but visible light. All right, so when you look at this number right here, what color would you tell me it would be?
No.
Violet would be the right color. So if you look, where do I have the spectrum? I have it somewhere right here. All right, where is the 4 times 10 to the 7th on the spectrum? It's right there, so it would be what color? It'd be violet. Is everybody okay with that?
So anything between,
Yeah, if it fell in between, it'd be violet. If it fell over here, it would be blue. It reads like a standard number line.
all right,
Okay?
What if it's
What if it's what?
in
exceed.
between, like right between blue and
Yeah,
black?
right there between.
Then you could put blue/violet.
No.
I wouldn't take off if it was on the line and you wrote blue/violet. That would be fine. I'm not going to be that picky. Goodness sakes. It's not that hard to get along with.
That's not about tomorrow. too.
Yeah. What, reading it? I
What
mean,
colors is it?
no, I'm going to let you use your chart to read the colors off the chart. I don't expect you to memorize the chart. I just expect you to be able to read the chart. That's all.
So nothing would exceed.
Now, you're expected to know this number and this number and be able to use the formula tomorrow. Yes. Now, what if I want you to find the frequency? So what would you do now to find the frequency?
I don't even know.
Yes, you do know. Which letter stands for frequency?
Oh, the V.
The V. So what do you do now?
Plug it into the formula.
Yeah, plug it in. So what's C?
Speed of light.
So we're going to plug 3.00 times 10 to the 8 in for the C, right?
Yeah.
And what'd you just find lambda was?
Nano.
Which is,
Wait.
are we going to use the nanometers that I gave you?
Yeah.
Are you going to use the meters that we found?
We use meters.
We got to use meters because it has to match the speed of light unit, right? So we're going to put the 4 times 10 to the -7 there, so the units match, and then times frequency. So if you were sitting in math class, what would you do to get V by itself?
Divide.
Divide by what?
4 times 10 to the -7.
Yeah. So that would cancel, and you'd have V or frequency, and divide over here by 4 times 10 to the -7th. And that was a little tough on my math skills, but it's probably going to turn out to be like times 10 to the 14th. All right, 7.5 times 10 to the 14th. And what unit do we learn goes on a frequency? So I put hertz on it. Like that.
So 4 times 10 to the 7th is the wave.
Yep,
Then, okay.
yep. This would be the frequency. because that's frequency. And this right here, we found that is the wavelength. And wavelength tells us the color.
You should use that gold color a lot. That's great.
It looks yellow to me. I don't want.
I was shooting for an orange. It didn't do too well, but I was shooting for orange.
I love orange. That's my favorite color.
I
I
think
don't
it
like
goes
actually.
How do you know something?
You are. Exactly.
I don't know.
All right. Do you think you can try one on your own?
Maybe it's an ill.
All right. Everybody caught up?
And I was trying to add on.
Wait, how did you get the foot?
How did I get the what?
I was just.
I plugged it in, but.
All right. Let me show you. Let me see what you punched in. No. There's where you went wrong, right there. Put your 3.00. Hit second and EE. Now say 8. Once you put that EE in, it knows times 10. You don't ever hit the times in the 10. Yes. Yeah, don't hit that. And then say divide 4, second, EE, -7.
I mean, for me.
Oh, you hit the wrong key. I do that stuff too.
What, coffee?
Yes.
I'm drinking coffee.
It's like hurt myself.
Ooh.
And then -7.
Like the calculator.
All right,
There you
Oh,
go.
okay.
There you go. All right.
I had a shot.
Everybody else okay with the calculator?
Yeah.
There we go.
Yeah.
We just did one like that. Let's go up higher. There, do that one.
Oh, man, that's hot.
I forgot. We were going to yesterday and I forgot one thing.
Don't worry about it. Come on. We're
Dang.
recording. Come on. Alexa and Isabel don't want to hear y'all yapping about Riverdale.
Alexa.
She's out for our class and Isabel's out for fourth period.
It's Belle.
Oh, I forgot she is recording. Gotta be quiet.
And Ethan may need it too, you know, since he's recovering from his traumatic event.
I doubt he will watch
Why
it.
do you
Well, he may not.
She's probably not awake yet.
So everything's gonna be to the -7 now.
Say what now?
Like the whole numbers?
Yes, the wavelengths are going to be 10 to the -7th if it's visible light,
All right.
because that's the range for visible light.
And so if it's E7, it's not visible light.
That is correct. So if they don't give you visible light, it will be in a different range. And they don't, and they don't have to give you visible light. The only thing is, so if they ask you color, you'll just say there is no color.
And can you just like move the decimal point twice?
You could.
Oh, okay.
I mean, really, if you wanted to, you wouldn't even have to do the color. You wouldn't even have to calculate the wavelength. You'd have to do the wavelength to be able to calculate frequency. But to do the color, you could just do 6.25.
Yeah.
And then tell the color.
All right. This is E.
Yeah. I think I did.
What did you do wrong?
I don't know. So would this be red or orange? So I got this number.
6.25 would fit where on the number line?
Oh, okay, so the big like.
Yes.
Okay.
Yes.
I got turned around.
You didn't change that to meters to match the meters of this number before you plugged in your formula to solve.
Okay, so.
It's got to be meters to match.
Oh, no.
This would be.
I don't think I did this right.
Then this would be.
1 times 10 to the right. Right here.
It's 3 times 10 to the 8, right?
Drive what?
Anybody from the drum line?
The drum line?
Yes.
I don't think so. I don't think I had anybody from drum line on third period.
All right, appreciate it.
Okay.
Never mind.
Are you in the drum
I'll
room?
go.
No, but
I'll go the wrong one. I'll put the speed of light instead of the 1
I said I'm
meter.
just playing, man.
Gotcha.
Don't love her.
What do you play?
She's me.
saxophone.
Okay.
Guess what I
Did your son go to that
No, he's in middle school.
Oh.
He plays the tuba. Yes. Sadly for us.
Does the like notes ever change in the tuba?
Oh, God.
All I hear is,
No, they changed.
Well, maybe they do at some point, but so far in my house, no. I haven't heard anything but that.
So my brother started guitar because he wanted to play an instrument since I play piano, and he
Oh, there's another one of you?
yes,
Younger?
yes.
Oh, okay.
but they're totally different. Like Emma's like,
Yeah,
then Sam is just.
anyway. So he picked up the guitar. He got me an acoustic guitar. Went and played because it was cool. And then so for Christmas he asked for an electric guitar. And now all we hear is like the very opening to the one that goes dun 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 dun
Oh.
dun. That's all he knows how to play. All he knows how to play. Like just those little bit, and so we hear dun 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 dun.
Can't be worse than the tuba.
He plugs it into his amp and turns it up all the way. And so like we can be sitting outside and then we'll hear dun, dun, dun.
Hey, at least you ain't playing inside. I put him out on the driveway of the day.
It's so funny.
Neither of my children were allowed to play the instruments in the house.
What did your daughter play?
Clarinet.
No, that's not that bad.
I was in chorus and my parents told me I was
Well,
not
if they're
allowed to
good at
sing
it, then it's not that bad.
That's so sad.
You
Okay,
got it?
people
Oh,
who
yeah.
don't
I
sing
do.
Alright.
guitar,
Fitting.
But I got it.
they makes me sad.
What does?
People who don't sing in the car, like when they have like music going and they're just kind of driving like,
I see.
I hate those people. You can't have fun.
Right. That's Andy.
All right, do we have an answer? What do we have? What's wrong?
I hate people who are silent in the car. Like they don't even talk. They're just
What do you got going
That's
on?
Andy.
Are you using your formula?
That's Andy.
Yeah.
I never have music in the car. And I'm just sitting there like,
where it's so awkward, you're not talking and they're just driving and
no, the real ones is like they'll be playing music and like you like start to
Not
see
so
you
loud.
and look at you like you're crazy. You're like, okay.
All right, so what do you put in for short? There.
Okay, I'm trying to
C
enjoy
is
myself.
always what?
Sorry you have no life. You're a little loser.
Okay, B is what we're solving for. So you need this. Now, I don't know what you got going on there. This has to be converted. So you're going to take that 625. You're going to change it into meters.
Bro.
Yeah, I wasn't here the other day, so I didn't know.
So nanometers has to become meters. So what goes beside nanometers?
Wait.
Is that bomb?
Isn't it 11?
1 times 10
Oh, 1 times 10 to the 9.
But the only
And
issue
what
is
goes
I changed
beside
like the color
meters.
Yeah.
of it to differentiate, but I printed it,
Oh,
I
one.
printed it here and then the color.
So
So like I told her, so I think she'll be able to like tell the difference, but it's not the same. Like I would have underlined it, but I would have counted on like the different color.
okay, you said times.
Your favorite
Right.
apple, that's the hardest. Yep.
Yeah.
Oh, yeah. There's some that are better last year.
Yeah.
So you got 6.25 times 10 to the negative 7.
But some of them were.
That.
And when I started songs that I love came away. Just going there.
Now, how do you solve for B?
She will, bro.
We have presentation.
All right, while Shatoria's finishing up her division, what did you get for B?
4.8.
4.8 times 10 to the 14. What unit did you put on it?
Hertz.
Hertz.
Hurts.
All right, what color was you like?
Orange.
Orange, very good.
So even if it's not that number, as long as it falls in the range.
As long as it falls in the range, yes. Anybody not get that?
Oh, they don't have to be named. You just have to differentiate the questions and answers. Oh, mine are all one. Okay, well, I think, yeah, as long as like you can tell.
Yes,
like,
very
run
good.
it back up and then have to question.
Yeah,
And I was
Alright,
Yeah, but
so
like,
find your
like,
hour.
just house,
And you
like, the
just,
one regular,
like,
phone.
He didn't even like look my way. He just stares up the car.
Okay.
That was
Where's
like,
6.25?
and he like turned.
Alright.
out.
Moving on.
I'm getting out. I'm walking out. I don't even want to see you anymore.
Alright, now for the weird part of the lesson.
Oh no.
Alright, the photoelectric effect is the really weird part.
This is already weird.
We haven't even got to weird.
It is like the.
Now, we said yesterday, Tuesday, that electrons can behave as waves and particles.
Right.
Now, I told you that we would talk about two examples where electrons could behave as waves. The two examples the state wants us to look at are the photoelectric effect and neon light.
Teachers, I apologize for this interruption. We need to just make an announcement this morning regarding the bandanas. Bandanas are not allowed even during Spirit Week. You should not have any gang-related or gang-color bandanas. That means black, red, blue, white, gray. All those bandanas are not allowed in this building. Should not be seen, should not be hanging out of your pockets, off your heads or anything. Please remove those and discard them or put them in your book bags immediately.
Do she realize that every color can be a gang color?
Right.
Oh, she realized that. I mean, like.
You guys wanna make.
Tie-dye
it-
My sister
Maybe
wore
you
a
should.
ribbon and I was like, you have to take that off.
Maybe you should point that out to her at lunch,
Yeah, I will.
in case it's unclear for her.
Like this tie-dye bandana.
I'm not one of her
signifies
favorite
my
people,
gang.
so I'm not gonna point that out.
See? I'm not even gonna get into her.
Alright, so the photoelectric effect is one of the things that we can talk about to illustrate how electrons can behave as waves and particles. Alright? Now, first of all, what is the photoelectric effect? So, it refers to the emission of electrons from a metal when light shines on the metal. Okay? Now, electrons, first of all, are in all metals. They're in all pieces of matter, whether it be our bodies, whether it be our desk, the pencil, the pens you're writing with, the lovely donut / muffin, whatever that thing is the queen has sitting on her desk. All right? Electrons are in everything. But the photoelectric effect refers specifically to metals. And light is going to be shined on a metal. When light is shined onto a metal, an electron is going to be ejected. Now, are we talking about regular metal? Yes. Are we talking about regular light? One would think so. However, if we just have a piece of aluminum foil laying here on the desk and we use plain old fluorescent light bulbs, do you think fluorescent light bulb shine on a piece of aluminum foil is going to eject the metal? No, and it doesn't. Okay, so there has to be something else going on. Now, the mystery of the photoelectric effect for scientists was what kind of light, okay, would do this. So, the mystery of the photoelectric effect involves the frequency of the light striking the metal. Would all light cause electrons to be ejected? Do all lights have the same frequency? The answer to that is no, they do not. Okay? The mystery of the photoelectric effect involved the frequency of the light striking the metal. Do all types of light have the same frequency? The answer is no, they don't. You're not going to. It gets worse. This is the easy part.
I don't understand.
I haven't done anything yet.
Wait, hold on, okay, so before we move on, let me clarify. Okay, so not a particle off of a piece of metal, the light hitting it has to be a specific frequency.
Oh, yeah, we haven't got there yet, but yes, we're going to. All right. All I'm saying is there's a metal. Okay. Light is going to shine on the metal, and an electron is going to pop off. That's all I'm saying so far. Okay. That's all I've said thus far. Okay. Now, Wave theory, as scientists knew it at this time, okay? At the time that they predicted that this would happen, they said any frequency would eject an electron. Now, did that happen?
No.
Of course not. A fluorescent light bulb like we use in this classroom is not going to eject an electron from a metal. The light bulbs you have at home in your bedroom are not going to eject an electron from aluminum foil in your bedrooms. Okay? So there has to be something else going on in order for electrons to be ejected from metal. The question is, what is going on?
All right, I'm trying.
You're really going to struggle today. I need you to throttle back and hang with me and work with me, okay?
Okay.
Okay?
Okay. I was just gonna ask. So light hits metal.
Uh-huh.
Electrons are ejected off of it. Is it like, have we seen, like, is this something that, like, a chemical reaction that we see every day, or is this like?
No, you have to do this. It doesn't happen on its own.
Oh.
So
No, they have to do this intentionally.
What's the point?
Wait, so this is.
What's the point? I have no idea what the point was or why you would want to do this.
Okay.
This was all done as part of research. This is all theoretical.
Maybe they got bored.
Right on
They
metal,
probably
metal.
did. I wouldn't want to do this
They
for a
looked at,
living.
they had down.
Okay.
They should make everything complicated for no reason.
But can you see this happen?
They could. I can't. I don't know how they did it. They just did.
That's why I
It
said.
doesn't interest me.
I trust you as a teacher, but I.
Why people want to do this, I have no earthly idea. Me in the slightest.
About the whole slide.
All right. Oh, it gets. If y'all think that first board is bad, y'all are in for a rough way to go today. Yes.
Can't repeat what you said, all of that.
Are you kidding me?
I don't, when I'm writing notes, I don't listen. Cause I.
You need to find a way to do both.
It's better if you just do it after.
I don't work that way. I got to do both.
I didn't do that.
Okay. So I will go back through it all after we've finished again. So only a certain frequency will knock electrons loose from a metal. So
So it's like it's being punched
essentially, you can think of it that way, yes.
and they just all fall out.
No, not all.
Most.
One.
So what?
Okay?
Oh.
Even though the metal is full of electrons. Think of it as the weak link. All right, one electron is ejected. Not a bunch of them, one. Okay, maybe two, but not a bunch of them. Yes.
It's like if you take a person and they're nice set of teeth, and then you take like different people and like those represent like different like frequencies, like they each like take a turn punching the person in the face. But, like not every person can punch a tooth out, but like then there's that one specific person who can.
One punch man.
Well, yes, but no, because they figured out how to get more than one to be ejected. And they figured out how to do it in a pattern.
I really don't know how
I was
somebody able to
expecting-
do it. How? Just how in the world?
I don't worry about how. They just did.
So
Okay?
this is even cool chemistry. It's windy chemistry.
I'm gonna let it.
What?
I'm gonna-
I find this cool and
They got more than one in a pattern. Just chill.
I like this.
Okay?
Of course he's German.
There's some other people too. Alright, so there was a German physicist by the name of Max Planck who proposed
Like,
Yeah.
like this.
that electromagnetic energy is not released continuously, but in small packets, or you can think of them as bursts called quanta.
Oh.
Hence the name quantum theory.
I feel
That's where it's
smart
coming
about
from.
this for some reason.
This is so. Why is this needed to be known?
It's a torture technique for teenagers.
Do you get this kind of hysteria every year with it?
Yep.
Actually, I
That's
don't.
why
I'm
you
like
This is one of the things they took out of the curriculum for about 20 years. And they put it back in several years ago. I have no idea why I would have left it out.
So on our final exam,
I have no idea. I've not seen the final exam in 5-6 years.
Not even a release.
okay, never mind.
Not even well, I've seen a few questions on a released exam.
I just don't understand
And
why
they want to
I'll
look
ever
at
need
it.
to know this.
You won't.
I
Physical
really-
science is a much more practical class. Unfortunately, universities still want you to take chemistry, so you're stuck with knowing this weird
I
stuff.
still gotta take.
I
it
really
college.
want to study more.
I'm never gonna know this when I get to college. I'm just like, it's gone by next
Yeah.
year.
I'm thinking of going.
My
into
grandpa's
maybe
a
as major,
physicist.
so, like-
And worked at RJR, and I don't even know this.
It's okay. You won't need it. It's cool.
It's cool.
Okay. Now,
He's probably one of those weirdos that like to do this.
Maybe.
Probably. He just
a quantum, which we're going to talk about in a minute, is a minimum amount of energy that can be gained or lost by an atom. Write it down, and then we'll go back so we can work with Ashaya here and her problem.
The quantum and the quantum theory.
Yes.
Will this be at our quiz tomorrow? Possibly.
I will stick to mostly Tuesday and just a tiny bit of today. Most of today will be on Monday.
So what will be tomorrow is probably like this calculating frequency and color stuff.
That would be fair game for tomorrow, yes. Some of what we'll do today would be fair game for tomorrow too. The harder parts of today, I will say for Monday.
So just everything that.
So everything is tomorrow.
I'll see if I can help you figure out which parts are today, which parts are Monday later.
Well, I'm going to die.
No, you're not.
I mean, everybody's gonna die.
Are we caught up?
We're all slowly dying.
Okay.
Actually, you don't really like start your body to your year. So we're still good.
So you're like 25, right?
Yeah, so you're 20.
Okay.
So we're still in.
And that's like your.
Ah.
Oh no, I'm almost done. I was in the
Oh, I thought y'all said you were all right.
I heard that phrase like yesterday. 20 to 50. I don't know where I heard that. I got it. Oh, it was. Oh, okay.
I heard psychologies are really cool.
Ah,
I love it.
whoops, that's not what I meant.
You know,
It's
Miss
great so far.
Boy didn't want
When I
to be
finished
in
this
honor
project,
psychology, and I was like really upset about
Whoops.
This year or last year?
it this year.
All right, we're gonna do one more slide, and then I'm gonna stop and go back so we can help Ashai with her problem and see if I can pick up some of my lost wayward children. All right, so not all of you are gonna be wayward, but some of you are going
So
to
a
be.
minimum.
So a minimum quantum of energy is required to eject an electron. Okay,
A minimum quantum.
of energy was required to eject an electron. So remember what we said a minute ago. Electrons are ejected from a metal. Regular lights in the room will not do it. It has to have a certain frequency. Max Planck figured out that minimum energy is going to be a quantum. He gave that minimum energy a name. He's calling it a quantum. Okay? All he knows at this point is it's a minimum frequency. He doesn't really know what it is, but he's given it a name. He's calling it a quantum. He knows it has to have some minimum energy.
So
The minimum energy is not defined yet by an amount. Okay? It's just a minimum amount.
So
Okay?
no, there is a minimum.
There is a minimum
It's
amount.
not defined.
It's not defined yet because is every metal going to have the same minimum amount?
wait, it's
No.
not
Wait, so theoretically,
I mean, it is defined, yes, but the problem is, you see all those blue metals over there?
Yeah.
Is every metal going to have the same amount? No, that's the problem. We can't say that the minimum amount of energy is, let's say, 100 joules, because every metal won't require 100 joules.
Alright, thank you.
Copper might need 100 joules, but titanium might need 150 joules.
Oh.
So we just say it's a minimum amount because the amount changes depending on the element.
wait,
So-
Does that help?
Yes.
Okay.
So the light is the minimum quantum energy
The
that
Yes.
hits the metal that ejects
electron.
an electron.
Yes.
Okay.
But if we have problems specifically about photoelectric effects, will they give us the minimum quantum?
No, you're not going to be able to calculate that at any point in time.
So
What?
it's light energy.
so theoretically speaking, if there's a minimum quantum of energy, is there also a maximum quantum of energy?
No, not at the
There's
moment.
not?
Not at the moment.
But
Alright.
that's like,
No, not at the moment. Stop. All right,
It's
Planck.
like affinity and.
Planck also proposed that there has to be a relationship between energy and frequency. Okay? If this light has to have a minimum frequency, it has to have an energy. So, what do you think the relationship is between frequency and energy? Any guesses?
Inverse.
Reverse. They're the same thing.
So, what do we call that in math class?
Equilibrium.
We're going to talk about equilibrium later down the road. Think math class. Inverse is opposite. So, what do we call them if you said same thing in math class?
same thing.
No, it's a vocabulary term. It's
What's the?
It starts with a D. Because y'all are all about some first letters.
Man, my math teacher was horrible, so I'm not even gonna
I
try.
was gonna say delta.
wait, no.
I'm going back.
Okay.
How are they related?
Shoot.
Oh, they're directly proportional?
There you go.
Ah, round of applause for Daniela.
Snaps.
Inversely means they're opposites. One goes up, the other goes down.
Oh, I'm thinking of.
You're thinking about wavelength and frequency, all right? Energy and frequency means they're directly proportional. If one increases, the other increases. Okay?
Because you need energy to have frequency.
Exactly. All right.
So it's okay.
So if your frequency of light goes up, the energy of light goes up. Okay? The higher the frequency of light, the greater the energy of the light.
I'm still waiting for that to talk.
The lower the frequency, the less energy of the frequency. All right, now, he also has an equation for this. I'm giving you the equation. We are never calculating the equation. That's not part of your curriculum, and I'm already way over the top in this unit anyways, but I'm not going that far over the top. Okay?
So I'm gonna get this.
I have every confidence you will get this.
Might die in the process when we get it.
Yeah, you are going to get it. All right, everybody there?
Yes.
All right. So, what's the equation he wrote to go with it? E equals HV. Now, E stands for what?
Energy.
Energy. H is a constant. It's called Planck's constant. I put the number there. You are never going to calculate with that number. You do not have to write the number down. I just put it there so you could see what the number is. All right. And V stands for what?
Frequency.
Frequency. Okay. And so E and H, which are energy and frequencies, we just said are directly proportional. H is his constant. Again, you don't even have to write the number down. It's just a constant. You are not calculating with a formula ever. Okay? Now, can I go back several slides once Ashai's caught up so we can see if we can help her make sense of it?
Sure.
So she's not writing and she can listen. Okay, write that down.
This is why I don't like science.
Why?
Stuff like this, when sure this might be true, but it's all theory, so we can't show you, but we can talk about it. But like that's
Love this.
Yeah, I love this stuff.
Oh, I have a question.
I warn you, tomorrow and when we get to the 4 quantum numbers, tomorrow, Monday are one of my favorite topics to teach, and you will probably not like it. But I'll have you caught up by, well, you might have to watch the video Tuesday because you're probably going on a field trip, but,
I'll be good for you.
I have a question.
yes,
That JS thing, is that joules per second?
yes. You there, Shy?
All right.
I told you you didn't have to write all that.
I wrote all
Go ahead.
All right, so if we cruise back to here. All right, you done writing? Now listen. So, the photoelectric effect is about light striking the surface of a metal and an electron being ejected. Will this kind of light cause an electron to be ejected from the metal? The answer is no. Okay, it's not going to happen. So all we said was scientists are trying to figure out what kind of light will eject an electron from a metal. According to current wave theory, that kind of light will eject an electron from a metal. But we all know, and scientists knew, that that shouldn't work. Okay? So the question becomes, how does it work? What's the problem? Okay? Why on earth will that light not eject an electron if wave theory says it should? So they're searching for an explanation as to how these electrons can be ejected from a metal. Are you with me so far? Okay. So, Max Planck, okay, tried to explain this. They knew that only certain frequencies would eject electrons. So you've got a metal. Let's just say it's aluminum foil. Y'all can all relate to aluminum foil. Okay? Light is shining down on the metal, right? And an electron is being ejected. But only certain frequencies of light are causing that to happen. Nobody knows why. So this cat from Germany, Max Planck, is saying that it has to be because they're only being emitted in small packets that he's calling quanta. Now, he's saying these quanta. Now, the only difference between quanta and quantum is singular and quanta is plural. Okay? That's the only difference in case you guys didn't know that. That's plural and that's singular. But they're the same word. Okay? But a quantum is just a minimum amount of energy. All right? So there has to be some minimum amount of energy that has to strike this metal. Okay? Now, this minimum amount of energy has to have a certain frequency. Okay? That's as far as we've got. Are you with me so far? So this minimum energy has to have a certain frequency. And then we got to here. Now we're here. Okay? Now I got to add a new vocabulary word so that somebody can get found out of shape. All right. Y'all's good friend Albert Einstein. He explained the photoelectric effect by proposing that light can be viewed as a stream of particles. Okay? So, he added to what Planck said. All right? So here's your metal. There's your stream of particles. All right. And then my artistic ability is not very good, but it will suffice. So Albert Einstein explained the photoelectric effect by proposing that light can be viewed as a stream of particles. Now remember, light is a wave in the old definition of light. So to view light as a particle at this time was pretty revolutionary. So Einstein is saying that light can be viewed as a stream of particles. So I've drawn little dots to represent the particles. So each of those particles now, according to Max Planck, carries a what? Each particle has to carry a quantum of energy. Okay? Now, if it carries a quantum of energy, it can do what? It can knock out an electron. And I'll let you catch up, and then we'll talk about it again.
What is the minimum quantity to be lost or gained? More of a quantum of energy.
Your minimum quantity of energy.
Minimum. So each particle of light carries a quantum of energy. What? Like, can you explain it again?
Yeah, let everybody catch up.
Hashtag
rules.
Are you gonna give us like homework for this?
Okay. That kind of.
What do you have to do with that? I
don't want
Yeah,
to work with
that's
this.
what I was thinking.
No, that's probably like calculating color.
Okay, I have one thing to say a little bit off topic. If it's gonna be this cold outside, I think they need to put on a little bit of heating.
The biggest thing I would tell you about my room between now and January is, bring a hoodie, a fleecy, something to, stay warm in here.
Does the heat not come
Because,
in?
I won't ask for them to turn the heat up in here because whose classroom's gonna get really hot? And they'll die. Who?
It's terrible when it gets too cold.
It is. And so out of respect for Miss Rector, we're usually a little chillier than we could be because they die. So, and,
Wait, who dies?
of course, folks. So,
They die.
you know, and I'm a little plushy, so I don't mind being a little cool over here. So y'all need to just dress warm.
On behalf of the chorus, I say thank you.
Yeah, I know. So, I don't mind being a little cool. So, bring a coat.
Wardell was
Okay.
cold too.
I feel certain that you've got something at home you can just drag around. So put it in your athletic bag down there. Bring it the first period.
Just go to the Hima's room, just stand in the doorway, get warm.
Yeah.
It smells bad.
Oh, it smells awful.
It's fine.
Oh, and it's terrible.
All right, is everybody caught up? Forget the smells. All right, so Albert Einstein proposed that light was a stream of particles. You with me so far? So each of these particles has a quantum of energy. You with me so far?
Yes.
Now, forget this part if it bothers you. All right? Now, each particle has to carry a minimum quantum of energy. If it carries that minimum quantum of energy, it can eject an electron from the metal. Are you with me on that? Okay, don't worry about the other part if you're with me on that. All right, I got everything there. Now, I want to get rid of a piece here that's going to bother you.
A photon?
This zero rest mass, because y'all don't need to know that. It's going to mess up the grammar, but get rid of that zero rest mass, because y'all don't need to know that part. All right, Einstein called, all right, each particle of electromagnetic radiation that carries a quantum of energy, a minimum quantum of energy, a photon. So if I draw my tacky little picture again, because I can draw it bigger.
I have a question.
Yep. Oops, hold on. I just turned the page and I didn't need to. Yeah, go ahead.
Is this photon charged? Is it like +2?
Uh-uh.
I thought that because it would like cancel out. That's the reason the electron pops up and replaces it. You know what I'm saying?
Well, the photon itself has no charge.
Oh, okay. So what's the whole point of the electron? Like, you've already explained this. Why does it pop up?
What are you talking about?
The electron, why does it pop up?
Oh, because the photon or these stream of particles cause the electron to be ejected. So the metal's going to wind up with a positive charge after the electron leaves it.
Oh, so it's just trying to change the metal.
It just winds up with a positive charge. All right. So, everybody with me?
No.
Einstein called each particle, all right, that carries a quantum of energy a photon. Now, I'm going to flip back just a second here, so catch up with me. I tried to draw neatly.
Do you recommend astronomy?
Yeah. That's why I'm, remember, if I go back,
Yes, it's stable.
a stream of particles, okay? So that's the stream of particles that Albert Einstein's referring to, right? That's why I drew it as a stream, and I've got multiple dots there. So if I draw this out to the side, this is our stream, and I'll label it again, of particles. All right, that's Albert Einstein's stream of particles.
I'm so used to just like writing 1910 because in Spanish she makes us write the like day instead of the month, and it's like weirding me out now.
It's okay, just keep writing it that way and practicing chemistry
How the
class.
rest of the world.
All right,
Now you're
Now.
right.
if this is a string of particles, based on what Einstein said, each of these particles carries a quantum of energy, so it's called a what?
Photon.
All right. Each of these is called a photon. And they carry a quantum of energy. Okay?
So
Theoretically, each one of those that strikes the metal can do what? Could knock an electron loose. Now, because Max Planck said that this was not continuous, did I draw them touching each other?
No.
No, I left space because Planck said it was not continuous, so I did not draw them touching. I left space between each of them to illustrate it was not continuous. Yes.
So the stream of particles is a stream of individual photons that can knock. So light is composed of a stream of photons.
According to Albert Einstein.
Okay.
So that's why it only pumps out one electron.
Mm-hmm.
It's not continuous. Gotcha. Gotcha.
Can I turn the page?
We're getting there.
Like,
Can I turn the
I
page?
actually like this.
That's fine.
This sounds cool. Yeah, you
Can I turn the page?
Yes.
Yes.
Okay.
This guy must have been really.
All right.
This is crazy.
So the energy of a photon depends on what?
Frequency
See,
of
radiation.
radiation.
There you go. Energy depends on frequency. Because remember, what did we say the relationship was between energy and frequency?
They're the same.
That's right. They're the same. They're directly.
Proportional.
That's right. And all this slide is doing is re-emphasizing what we've already talked about. There's nothing new on this slide. It is re-emphasizing what we've talked about. They are directly proportional. Nothing's changed. So, what I have right here, you already know. You don't need that. Whoops. You don't need that one. Why did it go away? I just wipe that out. You already have it.
I'm proud of you.
You're running it again?
Me?
Yeah.
Yeah. You can move on.
Okay.
Like, memorize already. I have to write things over and over with you to remember.
Okay.
Yeah, this is
That's
gonna be.
why I'm gonna write it again.
This
Oh my
is gonna
God.
be a unit that I'm gonna go home and like rewrite. Oh my
All right. Can I turn the page?
goodness, that works.
All right. So here, in summary,
I told you to do homework. I remember it.
all right, this just summarizes what we've already said for my people who I need to rewrite again. In order for an electron to be ejected from a metal, okay? In order for an electron to be ejected from a metal, the electron must be struck by a photon possessing a minimum energy required to knock it loose.
Oh. Is that the reason like lightning and you touch a metal and it like transfers?
That's conduction.
Boom.
Now, lightning static electricity and a metal is just a conductor of electricity. So the electrons travel easily through the tube. That doesn't have anything to do with this.
Oh, it doesn't.
Okay? But that paragraph summarizes what we just said. Okay? In order for an electron to be ejected, a metal from a metal, the electron must be struck by a photon. That single particle in that string. All those dots I drew. One dot is a photon. That single photon has to have a what of energy? A minimum quantum. If you have that minimum quantum of energy, you can knock the electron loose. Are you with me?
Yes.
Praise the Lord. Now, the last thing here is what we talked about when I talked about the blue elements on the periodic table. Do all of the metals require the same amount of minimum energy? No. Okay? There are lots of different elements, and because they're bonded differently, they require different amounts of energy. Okay? Some metals require more, some require less. So their quantums are going to vary. Okay, that's all that brown color says. All right, let me grab my stuff out of the back while y'all are catching up with me, because I need my stuff for the neon lights.
Are we playing with something?
Mm-mm. I am, but you're not.
Where's the fun in that?
There's no fun in that.
That's a weird
I
part.
feel like if I were to be a light, I'd be neon purple.
I was thinking like,
For me?
I just want to be like
I feel like
a
you'd be
Celestin with
sort of
I
fluorescent.
want to be the aurora borealis.
I feel like you'd be pink. Would I be?
turquoise.
I'm just kidding.
You seem more yellow.
Or,
Yeah.
yeah, yellow or like a really green.
I think green.
Yeah.
What about me?
Very yellow.
You would be like red.
Black. Yeah.
Okay, first of all, I hate the color.
You're hostile. Yesterday, that was.
I don't recall what happened yesterday.
I don't
I was
think
just
so.
like, what did I
You'd
do?
be an orange.
Oh,
Who is fault?
did you just say orange is ugly? Oh,
No.
man.
You would be.
No, she said Victoria did it.
What was Miss
Maybe I
Fault?
did it.
I'm not orange, I look like a giant pumpkin.
Oh, Janelle did it. Oh,
I'm purple.
oh.
You're blue.
All right, are my two writers that are slow caught up?
Almost.
Hey, Mario was
Nasty.
white.
You'd be like. Yeah,
Yeah.
Mario would be gray. You'd be
Nah,
white.
he'll be, yeah.
I feel like I'd be like a pastel blue.
No, you
or
would
pastel
not.
pink.
You
No,
were
you're not
red
being
because
on
you
my
were
side.
hostile.
I am not.
Look at that. You slapped your hand. Hostility.
I'm trying to prove a point. I don't
Queen
know.
just thinks you're nuts.
Okay, not that
You gotta
far.
pull the gun out.
All right, this
I'm
one.
not
Guys.
Yeah, I want to be
I
neon
actually really
Huh?
nice to me.
No, we're not done.
I'm not
See
still.
those?
All right. Moving on.
Yeah, see, I'm
Neon lights.
not-
Yeah, you gotta draw that.
My notes are-
It's a couple boxes with some
Yeah,
lines
I
and
The
a,
thing under it.
those are humps. Now, the lovely drawing there represents this lovely neon light that I have here in my hand, okay? Now, it's nothing more than a glass tube, and the one that I have in my hand, I think is hydrogen.
Oh.
Yes. All right, I have hydrogen gas in my hand, okay? Currently, the hydrogen gas I have in my hand is in the ground state, all right? It is the state of lowest energy. Okay? These electrons are doing absolutely nothing. They are completely chilled and they are doing nothing except moving around in here at a slow rate. Now, I am going to put them in this lovely box on my desk. I'm going to pass a high voltage current through it, and they're going to move to the excited state, which is a state of higher energy. Notice I did not say highest. I said higher energy because there are multiple levels of higher energy. All right? So, they're going to move from the ground to the excited state. Now, when they do this, they're going to absorb. Energy. And then when they get there, what are they going to do? Are they going to stay there?
No.
No. They're going to come back down.
Oh.
Okay? When they come back down, they're going to do something.
Absorb E.
They're going to absorb energy. E is the universal symbol for energy. Let's see if it'll work. This thing was having difficulty last semester.
Oh my God.
All right, so.
There's me at the top and the bottom.
All right.
And in the middle.
So when
Oh,
we pass a high voltage current through the hydrogen, all right, what happens when the electrons come back down?
it goes. It's just.
It will go back up, but what happens when it comes back down?
It goes back to its lower state.
Yes, and it produced
Nothing.
Light.
light. All right, it released, or we could say emits light. Now, light is a very generic term because this is visible light, right? Does it have to emit visible light?
No.
No, it could also release any type of EMR. But I opted to show you an example that is visible because if I release something like a microwave ray, y'all would just stare at me and go, yeah, right, Miss Wall, we can see that. You're just making that crap up. Okay? So I'm showing you something that you can actually legit see instead of just staring at it going, right. Okay? Now, once it gets to the ground state, where does it go?
It goes right back up.
Right back up and then right back down.
So
This is a continuous loop of ground excited, back down, up, down, up, down, up, down, up, down to give you that neon light.
So you have a big fluorescent like is in there. Is that why when they get old you can see the light kind of?
And you can hear it right now, like you can hear the buzz sound in this one.
Wait, and when you said whenever they get old, they do what?
Well, and like when they're new too, but when they get old you can see it more because like they become slower. So, like turn on and off, so like you can kind of see it like flickering and like it moving.
I love that.
I hate the sound of the light. I hate it.
All right, we did that.
No, I'm talking about
We don't need that.
Oh,
All right,
I didn't hear it.
now, when light passes through a prism, you guys know this because you've seen it for years. What do y'all see when light passes through a prism?
Rainbow.
Okay. Y'all can say the rainbow for the time being because we're not very sophisticated at the moment, but we need to fix that.
Oh, RGB.
Okay, I will accept RGB at the moment because, again, we're not very sophisticated. We need to fix that.
All right, so we get technical.
I want the technical answer.
Visible light.
All right, that's the answer I want.
Oh,
Hey,
All
can I
right.
say the name?
All right.
Hey.
And I'd even like to improve on that. No, because I'm all about some vocabulary. Woo. I was just trying to close out the band, not give you access to the chorus. They get a
Solar
little loud.
spectrum.
Hmm?
Spectrum.
All right, so let's change it to the visible spectrum. Okay?
Huh? What?
All right, so we can see the visible spectrum when you do that. Now, All right, so we just answered this. This is that, so we don't need this. We just answered that question. All right, now, what determines the color we see? Why do we see red? Why do we see blue? Why do we see orange?
The
The optical lobe.
wavelength.
Exactly.
Actually, it's the optical lobe back of your brain.
We're not going to talk about the art reasons. We're just talking about the science reasons. Okay? I hope we covered that earlier today, but I was like, maybe we didn't do it well.
You want to go to like a 70s club.
You want to what?
A 70s club.
Have a good time.
Thank you.
Big ID.
All right, everybody caught up?
0 at the time.
Got
Or negative
Emma,
30.
you know, what year was your mom here?
Like 19, she graduated in like 87.
You sure recreated that picture she had?
No, I'm going to.
Oh, you are?
Yeah. That's the day.
All right, the last thing that we're going to do so that I know where I need to pick up tomorrow, so put this in your notes, is to talk about what happens when we look at hydrogen through a prism, which would be what I have right here, all right, through a prism. And that's why we have that lovely chart on the door over here. When hydrogen gas goes through a prism, you see what you have on this door over here, okay? Hydrogen gas is the second one from the bottom. What do you have right here? Do we see the rainbow right here?
No.
Mostly what you have is black, okay? You have two blue lines, one that's a little lighter blue and one that's red, okay? So you have a blue line, one that's a lighter blue, and one that's a red line. And everything else is black, okay? This is called a line spectrum, okay? So why don't we get Roy G. Biv here? Why don't we get the same thing?
Because it's a gas.
Okay, it is a gas. Tell me this, what determines the color of light we see here?
Wavelength. So
Still determined by wavelength.
Maybe it only has a certain amount of weight.
Will frequency.
Its minimal wavelength is 4.9 times 10 to the 7.
Okay. This light, all right, has a different frequency and wavelength. So you see a different spectrum.
Is that first color dark blue?
Okay, so what?
Is that first color dark blue?
Yeah, it's just a darker blue. It doesn't necessarily have to be a seriously dark blue though. Now for homework, I'm giving